Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem cherry pickup 2. This is definitely a hard one, but it's not crazy hard. At least in my opinion, it's not as hard as the first one, which is why I'm not going to recommend that you solve the first one before this one. This one, in my opinion, is easier. So we're given a matrix. Let's just focus on the visuals here. And we have two robots. They start at the top left and the top right of the grid. And for each robot, we have three choices on every move. We can either go down left, down, or down right. And the other robot makes the same, or not the same choice, but it has the same set of choices to make. So it can go here, it can go there, or it can go there. So maybe this one goes down, this one goes over here. And they both make choices at the same time, so they're always going to be in the same column. Now, given this, each robot picks up all the cherries or whatever thing you want to consider. It takes the value in the position of the grid that it lands on. And we want to determine the paths of both of these such that we maximize the points or the cherries that we collect. And that's what we want to return. So in this case, you can see the paths are going to be like this, and here like that. So the total for this is going to be 24. Now, they also tell us that if both of the robots land on the same position, then both of them can't pick up the value. Only one of them can pick up the value. So you might think we need some additional logic to handle that. But my claim to you is that we are guaranteed every value in this grid is going to be greater than or equal to 0. Why would we ever want both of them to land on the same position? That would never lead to the maximum result because we are guaranteed the grid is always going to have at least two columns. Why would I ever want this value to be in the same position, even if there's a big value there, because they both can't collect it. So I'd at least want this guy to collect something over here. It'll get something that's greater than or equal to 0. And if both of them were to land in the middle, our set of next choices would be limited to only 3. But if I have one over here and one over here, now my set of choices is going to be at least 4. So again, why would we ever want them to land on the same position? Next, we kind of think about this in terms of choices. It's not hard to kind of visualize this as a decision tree because that's kind of what we're doing. You might think before going down the brute force method, the backtracking solution, you might think, is there a greedy way? Don't we just want the robot to pick the maximal of its choices? Not necessarily, because what if this guy says, okay, I want to take the 5 because there's a 1 here and there's a 1 here. But what if there's 100 over here? We can't be greedy and take the 5. We have to take the 1 in this particular case so we can then get the 100. No point in trying to be greedy. We do have to consider all possibilities. We don't know what lies ahead. Now, when you think about the brute force, you think, what are the parameters of the brute force going to be? The base case is kind of obvious. Once we reach the last column, we can't really go any further. And we do have to do this simultaneously because we do have to make sure that both of them don't land on the same position because we definitely don't want to overcount the solution. We don't want to collect the same value twice. So we do have to maintain what is the column of the first robot. I call that column 1. Column of the second robot, I call it column 2. Now you might start to be naive. You might start to think we need another parameter row 1 for the row of this robot and another parameter row 2 for the row of this robot. But remember, it's easy to miss this. They are always in the same row, so we only need a single parameter for the row. This is actually enough when we take this brute force solution and optimize it with caching, which I'll show you how to do in the code. We can actually pass this problem. That's why it's not like a crazy problem, in my opinion. Now, what does the decision tree look like? For a single robot, we have 3 choices. But we have to make a choice with 2 robots. So it's not that we have 6 choices. Let me make this very clear. We don't have 6 choices. We have 9 choices. 3 times 3, because we consider the case where this robot goes here and this robot goes there, or the robot goes here, or the robot goes there. That's 3 choices. The next 3 would be this. Go down, this one goes here, or here, or here. That's another 3 choices. And I could continue with the rest of them, but you get the point. That's what we will consider as well. And then let's consider one possibility where let's say we go here and then this one goes here. Next, we will recursively make the same 9 choices. In terms of time complexity, this looks like 9 to the power of how many columns we have, or the number of rows. Sorry about that. I always get those confused. So it's going to be something like this, 9 to the power of r. Of course, we want to optimize this. We know the parameters are going to be row, column 1, and column 2. What are the possibilities for this? Well, r could be the number of rows. I'm just going to use capital R for that. For each of these, it's going to be c, so times c squared. That's the time complexity. That's also the number of subproblems. So this is the size of our cache when we apply caching. When we get to a subproblem, we don't always want to recompute the result, so we store the result of it in the cache. Okay, let's code this one up. Let's start with the DFS. It's the recursive brute force solution, and I'll add caching to it at the end. So we have the row, column 1, and column 2. The base case is, well, the main base case is going to be when we reach the last row. So if r is equal to number of rows minus 1, I should probably compute that. So we have number of rows and number of columns. I like to do this just because it makes things more readable. That's also why a lot of people you'll see will use I and J for rows and columns, but I think that's less readable. It's very, very clear what we're talking about when we have R and C. So I prefer this. This base case is when we reach the last row. In that case, we are just going to simply return the sum of the values in the positions. We know they're both in the same row, so we can do it like this. The value at column 1 and the value at column 2 from the grid. But what if they were the same? What if column 1 and column 2 is the same? We probably need another base case to check that. We don't want to overcount the solution, like I said. So let's check. If column 1 is equal to column 2, let's return 0. Let's just not consider that. It'll make our life a little bit easier. But there are other cases where we might want to return 0. I didn't talk about it in the drawing explanation, but what if we go out of bounds? Well, the row is never going to go out of bounds. We keep moving down until we reach the last row, but the column could go out of bounds. It could be that the column 1 or column 2 is less than 0. And the easiest way to check that is take the minimum of both of these. This is kind of a shortcut. Take the minimum and check, is the minimum less than 0? Or opposite, take the maximum of both of them and check, has that gone out of bounds? Is the maximum equal to the number of columns? That's the only way it would go out of bounds. If that's not the case, let's go ahead and compute the result. So I'm going to compute the result, initialize it to 0 actually, and then out here, we're going to return it. But now's the fun part. How do we enumerate all of those 9 decisions? I don't want to write 9 recursive calls. So the easiest way to do this is 2 loops. I'm going to call this C1D, the delta or the difference in C1. We know we can either move the column to the left. I'm going to call that -1. We can either keep the column the same. I'm going to call that 0. Or we can move to the right. I'm going to call that 1. And we can do the exact same thing with column 2. So just have this hard-coded array. I probably could have saved a little bit of space, I guess, if I put this in a variable, but it really doesn't matter. Now is the recursive call. When we call DFS, what are we supplying here? Well, the row always increases by 1. That's the easy part, row plus 1. What about column 1 and column 2? Well, that's why we have this delta. Column 1 is now going to be C1 plus the delta, and C2 is going to be the same, C2 plus the delta. And we're trying to maximize the result, so let's just set result equal to the maximum of the result and the maximum of the recursive call. There's one thing I missed here. As we are traversing the grid, shouldn't we pick up the cherries at this position? So far, we only pick it up in the base case. I should here be adding to the recursive call this value right here. But that's going to make this line really, really long, so I'm just going to choose to do that here. Before we return the result, let's just go ahead and add this to the result, because we know this is a constant and it's going to be added to every single call here. So instead of doing that here, I'm just going to do that out here. So result plus equal to this, and then return it. This will pass. Let's just finish it up. So when we call DFS, the row starts at 0, column 1 starts at 0, and the second column starts at the number of columns -1 all the way top right. So this does not pass, but we can just add a little bit of caching and then make it pass. So I'm going to declare a hash map for that. And here I'm going to add the if statement. Is this key already in our hash map? If it is, go ahead and return it. If it's not, go ahead and compute it and then return it. So when I compute it, I'm actually going to store it right in the cache. So I'm going to do this now, result plus that, and then I'm going to return that just like this. And it looks like I have a little typo here. Don't know why I put R1 here. We also have R1 up here. Sorry about that. We also have a little typo here. I forgot to take the maximum of these. We don't want to assign the result to a tuple. And another R1 here. But other than that, let's run the code. And you can see it works, and it actually is pretty time efficient. This is about as time efficient as you can get it, but we can improve the memory. So right now the memory is 3-dimensional. It is going to be the number of rows times the number of columns squared. We can actually improve that because you notice if we're computing this problem, we only need the result of the subproblem from the next row. This row depends on the next row. We don't need every single row in memory at any point in time. So when we implement the tabulation method, we can improve the space complexity to actually be C squared, the number of columns squared. Let me show you how I'm going to do that. So I mentioned that we don't need the memory for every row to be in memory at the same time. Instead of going recursively, we compute the solution top down. We can work our way up. We can compute this bottom row. What is the subproblem of the bottom row? It's basically if robot 1 and robot 2 were to be in any combination of those positions, what is the maximum result we could get? For example, consider if robot 1 is here, robot 2 is here. To compute the value that goes here, we would recursively, well, not recursively, but in our solution, we would try all those 9 possibilities I talked about, but we'd kind of go out of bounds, wouldn't we? So let's just implicitly put a bunch of zeros here so we don't have to consider the case where we go out of bounds. This way of visualizing it is not entirely enough, actually, because what we found is our space was 3-dimensional and we reduced it to 2-dimensionals. At least that's what we're trying to do. And that 2D grid is going to look like column squared. It's going to be the number of columns, which in this case is 3, and we're going to square that. So 3 by 3. Now, what does this represent? Let's say this is column 1, this is column 2. We're basically saying if robot 1 is at column 0 and robot 2 is at column 0, what is the result going to be? Well, we skipped that because we don't consider the cases where they are equal, remember? So that's easy enough. What about when column 1 is at 0 and column 2 is at column 1? That's going to be over here. In that case, it looks like we'd get a 2 plus 1, and then we'd put a 3 over here. And we can do the same thing here. In column 1, we have a 2, and in column 2, we have a 1. This is column 0, sorry about that. So here we'd also put a 3, and you'd kind of just go through all of them and do all of that, fill those values in. Even though it's really hard to visualize this because this is 3-dimensional, we're going to have these stacked on each other, and we're trying to reduce that now to 2 dimensions. So what I'm saying is, okay, we compute this first one. I'll just kind of fill these values in. 1 and 0 is going to be the same as 0, 1. So we'll put a 3 here. 2, 0 is going to be the same as 0, 2. It doesn't really matter which robot is in which position, so we'll have a 3 here. 2, 1, 1, 2 are going to be the same, which is going to be 1 plus 1, and that's going to be a 2 here and a 2 there. So at least in the last row, if we were trying to maximize the result, the most we can get is a 3. That's what we've discovered so far. Now, one more optimization I'm going to make. If we were trying to fill in this grid, we'd need 2 nested for loops iterating over the number of columns, right? But we actually don't need that. I'm hypothesizing we can actually only fill in this part of the grid and skip that part. It doesn't really improve the time complexity. This is still proportionate to C squared, but it's just an easier way to code it up, and you'll see that when I code it up. Basically, what I'm going to say is for C in range from 0 all the way up until the number of columns minus 2. And actually, I think even this is more than we would need, because when you look at the picture over here, would we ever want the 2 robots to cross each other? Would I ever want this robot to end up on the other side of this robot? Probably not, because it doesn't matter which robot picks up what. We care about the total that we pick up. So if we were ever able to create a path like this, we could have done the opposite and created a path like this. So why would we ever want the robots to cross? This is something that's not super important, but knowing this can actually make the code a little bit easier to write. So that's what I'm gonna be doing. So this is what we computed for the last row. Now let's compute the next thing for the next row. And I'm not really going to do a lot of it. Let's just consider this one because we know this is what ends up maximizing the result. So where robot 1 is at column 1 and robot 2 is at column 2. So we're looking at this and this. So how do we get the value that goes here? Well, we of course take the values existing in the current position. So we'd find a 5 here and a 5 here. We are keeping track of another variable. Remember the current row that we're in. We're working our way up as we do this. And remember, to compute this row, we only need this row in memory. And the word row is misleading because the values for this row actually are represented in a two-dimensional grid. So what I'm saying is, let's say this is our DP grid, our previous DP grid, and I'm right now computing the current DP grid of our current row. Also, I think I was wrong when I said we're at this column. I'm sorry, I don't know what I was thinking. Robot 2 is here, of course. It's at column 2. So we actually want the value that goes here. But yeah, the first thing we do is take the values of this, that's 10. And now we want which one of the subproblems was maximal. Again, that's 9 different possibilities. So basically we look at the grid. And just so you know, coincidentally, the size of this grid is 9. And that's because the number of columns is 3 times 3. That's not always going to be true. It could have been possible that this grid was 5 by 5. Even if the grid was 5 by 5, we still only have 9 other choices that we would be looking at. I want to make that very clear. This is simple for us. We have up to 9 choices to look at. And those 9 choices would be basically this, or this. We really don't have many choices. There's really actually only 2 valid choices. Either robot 1 goes down and robot 2 goes here, or robot 1 goes here and robot 2 goes over there. All other choices are invalid because we don't consider when they're on the same. We don't consider when one goes out of bounds. So there's 2 choices and it looks like this one is maximal. Where is this stored, by the way? In 0, 1. 0, 1. The value is 3. So we take what we computed, which was 10, plus 3, and store that in this position, which is 13. So that's what you would pretty much do, filling in this entire grid, pretty much. Now, since we only want 2 of these in memory at a time, we would take all these values, move them up here. This is our previous DP, and now we'd compute the next one, our current DP, as we work our way up, as we get to this row, and then eventually this row. When we're finally done, what value are we going to return? Well, we know we started here and here. So whatever our DP array ends up being, we will return the value that is right here. Column 1 is 0. Column 2 is the last column. So this is all the memory optimization and the tabulation solution. Basically, the space is going to be number of columns squared. Let's code it up. So I'll leave this code here, but we aren't going to be reusing any of it. But sometimes when you're writing the bottom-up solution, referencing the recursive solution can be helpful. First thing I'm going to do is just declare our previous DP grid. And like I said, I'm going to default assume that they're all 0. So we're implicitly saying every value below the last row is implicitly 0. So just like that. And I want to work my way bottom up. Some people don't like that because you have to go in reverse order. So this is what I do. You don't have to write it that way, but then if you write it the other way, you end up changing the logic of the problem kind of a lot. And that makes it very different from the recursive solution. That's why I prefer doing it this way. But again, you don't have to. Now, for this row, we're trying to compute the current DP. So all I need to do is just copy that and assign it here. Okay, so next we want to enumerate all of the columns. So column 1 could be in any of these valid columns. Column 2 could also be any of these valid columns. But like I said, I want to take a bit of a shortcut. I know column 1 is never going to cross column 2, so why don't I just put columns minus 1 over here. For column 2, I'll put column 1 plus 1 because I don't want this to start at column 1. That would mean they're at the same position. Then I go up until the number of columns. This way, not only do we not consider the case where they've crossed each other, which would be redundant, but we also don't consider the case where they overlap. We don't need an if statement now to check if they overlap. That's pretty convenient. I even would consider that pretty neato. So now for this subproblem, we want to compute the number of max cherries. And for us to do that, I'm going to assign this to 0. And after we have computed the number of max cherries, we want to store it in the current DP grid. And what is the subproblem that defines the current DP grid is C1, C2. I don't need to put the row here because we automatically know current DP corresponds to the current row. The previous DP corresponds to the previous row, aka row minus 1. But how do we enumerate those 9 decisions? Well, how did we do it recursively? It looks like I just had a couple nested for loops. I can just copy and paste that. It's just that easy. Now we're getting 5 layers of nesting deep, so I might as well show you a bit of a shortcut that I actually learned today. We can take these C1, C2, and we can enumerate them by taking the product of 2 arrays. So I put the first array as this, and the second array is going to be the same. So when we say product, we're just considering all combinations of this. The first of them is going to be assigned here. The second is going to be assigned here. So it's pretty much doing what we had earlier. We just don't need to do one extra layer of nesting. With this delta, I'm actually going to put the new columns in separate variables because we're going to be needing them many times. So just like this, column 1 and column 2. Now, while we don't need to consider the case where column 1 and column 2 are equal, we kind of do need to consider the case where the new column 1 and new column 2 are equal, don't we? Shouldn't we consider that case? No, because for this, if we try to reference current DP or the previous DP, the value stored there is going to be 0 because we never assign it in the first place. We never consider that possibility. So we don't need to consider when the column or the new column are equal, but we do need to consider when the columns go out of bounds. New column 1 could be less than 0. New column 2 could be less than 0. Actually, it can't because we guaranteed that's not going to be the case. They never cross each other. Column 1 is always going to be on the left. Column 2 is always going to be on the right. This simplifies things even more for us. Now we check, is the new column 2 equal to the number of columns? We don't need to check if column 1 is, it never will be. If that's the case, by the way, we just continue, we skip that. If that's not the case, we want to compute the max number of cherries. Well, what's the current number of cherries? It's going to be grid at the row, column 1, plus grid at row, column 2. And we can probably just move this up because this is not changing within this loop. We're using the original column. So I'm actually just going to take this and move it up. This is the current cherries. This is the max cherries. Now to compute the max cherries, we can say max cherries is going to be equal to the maximum of itself or the result of the number of cherries in the current position plus the subproblem. This is surprisingly the easy part. How do we know where the subproblem is? It's in the previous row, aka the original DP grid, and what are the coordinates of it? Is it column 1 and column 2? Or is it the new column 1 and new column 2? Well, if we're starting at column 1 and column 2, and this decision represents the subproblem, we have to consider all 9 valid subproblems, then of course we want to do the new column 1 and new column 2. And if you look down, that's exactly what we did in the recursive solution when we call DFS. So nothing crazy. Lastly, we want to out here, before we do that, over here, current DP should be assigned to max cherries after it's been computed. And also we always want to update our previous DP with the current DP after it has been computed. So just like this. And what is the return value again? Well, it's going to be stored in DP. The coordinate is going to be the first column, starts at 0. Last column starts at number of columns minus 1. So this is the entire code. A lot of work. Usually the tabulation method is not this much code. I mean, there probably are ways we could make this more concise, but I didn't want to make it too unreadable. So hopefully you can translate this into other languages if you're trying to do that. Let's run it to make sure that it works. And it does. It's pretty efficient. You can see for once Leetcode is actually accurate, this solution is definitely memory efficient. If you're preparing for coding interviews, check out neetcode.io. Thanks for watching, and I'll see you soon.